work done is, let's say, magnitude-wise area under the curve. Integral PdV, right? So clearly this area will be more magnitude-wise, that big fellow. And this one would be small magnitude-wise. So if a gas is taken from one point to the other point, V1, P1, T1 to V2, P2, T2, then work done is different in the two cases. That is the important point. Work done is different. But internal energy depends on the temperature. In the two parts, temperature difference is the same. T2 minus T1. Temperature difference is the same. And therefore, delta E is going to be the same. Just think about the energy formula for gases. You can refer to it right now. You can see the dependence of energy on temperature. So in the two parts, the internal energy change is the same, but the work done is different. Right? If this is same, and if W is different, then it means Q will be different. That means to change the temperature from one value to the other value, you cannot say you need the fixed amount of heat. Think about copper. Copper at 25 degrees centigrade. That is to be heated to 35 degrees centigrade. You don't worry about different heat. 25 to 35 copper, same heat. That's because in case of solids, this works very nicely. Q does not depend on the path. Here, when you are dealing with gas, Q is depending on the path. Now, what do I say? For specific heat capacity, how do I talk about specific heat capacity of a gas? How can I say specific heat capacity of carbon dioxide is so and so? A question will come, which path? I can say specific heat capacity of copper is so and so. But when I say carbon dioxide, which path? This, which path? Because Q depends on the path. How you actually carry out that process in case of gas. Pressure, volume, temperature. That's the thing about gases. You cannot talk about Q unless you talk about some specific process. And C depends on Q. C depends on Q. Whether you talk of per unit mass or per unit mole. This is per unit mole, this is per unit mass. For gas, we prefer per unit mole. That's one thing. Second thing is the path dependence. So therefore, in case of gas, either you say every unique process has a unique value of C. Then imagine how complicated the life would become. Every single process that a gas undergoes, for that you will have some value of C. Whereas C for copper is given in text, C for iron is given in text, you will never be able to find such information for gases, because every time there is a process, there is a unique C for that process. So to make our job easier while dealing with gases, we have come out with two C's which are for specific processes. But the good thing is that other processes can be handled by using these C's. And one such C is called CV. CV is for the constant volume process. Keep the gas inside some rigid container which will just not change its volume. Now heat it. Do whatever you want. Second thing is that you keep pressure constant. You keep pressure constant. Let volume change, but pressure would not change in this case. So now we have two processes defined, and for these two processes we are defining two C's. One is CV, other one is called CP. So this subscript shows heat given at constant volume, heat given at constant pressure, right? That is why for gases you come across such CP and CV type of things, and in solids you just come across C, right? When we do some analysis, we find this relationship in CP and CV. So at this point of time you will have to take it for granted that this is valid, but this proof will be covered in physics. When this topic heat is discussed, then there will be a proof for it, Cp equal to Cv plus R. At this point of time you must memorize it. This is very, very important relationship, Cp equal to Cv plus R. Now that also means that that Cp has to be more than Cv. So Cp is more than Cv. Any questions up to this point? Let me know. Yes, I can see that private message. R is the gas constant. R is the gas constant. Yes, anything else? This background is essential to discuss adiabatic process. We were discussing various processes, right? Now, the ratio of Cp to Cv, that ratio is denoted by gamma, and you see gamma whenever you see discussion of adiabatic process, you see gamma. So to understand gamma you need to understand Cp and Cv, and that is why all this at this point. Now what is adiabatic process? Adiabatic process means that you have heat insulated container. You have heat insulated container. Think of ideal thermoflask where coffee is kept, ideal. In real life, coffee will become cold after some time. But think of ideal thermoflask where hot coffee remains at the same temperature forever. That means what? From inside, no heat goes to the outside. And vice versa also. From outside also, no heat should come inside. So, adiabatic process means there should be absolutely no transfer of heat taking place. When we talk about isothermal process, we talked about it I think in the last class. Practically, how do you make it possible, isothermal process? Suppose some heat is getting generated in this chamber and you want to maintain constant temperature. How will you maintain constant temperature even if some heat is getting generated? You will make the walls so nicely thermal conducting that if heat is getting generated inside, it will simply go to the surroundings. So if inside temperature was something, even after that generation of heat is all gone through the walls. Temperature is still the same. So one can maintain isothermal process in this way by choosing such container walls which conduct heat very nicely. On the opposite, if you don't allow heat to travel at all from the container walls, up, down, everywhere. Then there can be, whatever happens remains inside. Adiabatic process means there should be no transfer of heat in any direction, right? So if we apply first law of thermodynamics, then this Q fellow will be nothing, 0, right? It will be 0 in adiabatic process. So you would have delta E equal to W. Before I discuss further, if you have any question, then let me know. Alright, so let's proceed with further mathematics and arrive at a result, just like we arrived at a result for isothermal reversible process. Now we are going to find out some relationship for adiabatic reversible process. Reversible means slowly it is being carried out. Now we want work done, and work done is given by integral pdv minus sign from V1 to V2. Now let me also tell you that in adiabatic process these relations are also valid, again without proof. In fact, if I tell you one, you can get others on your own. If I tell you only one, others you can get on your own. Just remember PV to the power gamma is equal to constant. This is valid for adiabatic process. This does not mean that ideal gas equation is not valid. This is an additional law, PV to the power gamma equal to constant. So PV equal to nRT you will be using. We'll be dealing with the ideal gases. So when you use PV equal to nRT and the PV to the power gamma equal to constant, then you are able to get other relations that I was talking about. Relationship between temperature, volume, relationship between pressure, temperature. So these two relationships can be very easily deduced by making use of PV to the power gamma equal to constant and PV equal to nRT. It is gamma power is on V, otherwise I would use bracket. Power gamma is only on V, not on P. This is additional relationship. So we will be talking about ideal gases and you can use PV equal to nRT. Only in gaseous state topic in chemistry, when we discuss real gases, van der Waals discussion, that time we talk about real gases. Otherwise, whenever we discuss heat, whether in chemistry or in physics, we deal with ideal gases. So PV equal to nRT you can use. Now, we want this, and we can't take pressure outside the integral. That's why all this discussion. Delta E equal to W or these things, PV to the power gamma equal to constant. This is to make us solve this. So, as far as that integral is concerned, pressure and volume, pressure is not constant. And if we try to use pressure into volume equal to nRT, and if we try to put pressure equal to nRT upon V, then temperature is also variable, volume is variable. So even if you try to replace pressure by nRT by V, in isothermal it was very easy because temperature was constant. Temperature came out of integral. In adiabatic, temperature can change. Temperature can change inside the system, right? Heat transfer is not taking place. So temperature can change inside, and volume can also change. So you can't integrate even after that. So we go for indirect method, not direct method. This is the indirect method. W is equal to delta E. That's indirect method. So what is, let's talk about DE. DWD. What is DE? What is DE? Look at the definition of CV. Now, consider some constant volume process. I'm trying to prove one result. So for that, we start with the definition of CV. CV is defined as Q at constant volume upon N delta T. Right? That's the definition of CV. Now consider some constant volume process and apply first law of thermodynamics for that process. What is W at constant volume? Zero. When volume is constant, there can be no work. That means delta E at constant volume is Q at constant volume. So, but Q at constant volume is NCV delta T. Delta E equal to NCV delta T. Now, once we have DE equal to NCV dt, we don't want CV. We will have to integrate it to find W. We don't want C at constant volume. Can you get rid of CV from these two equations? In other words, can you find CV in terms of gamma and R from these two? I can see that private message, CV equal to R upon gamma minus 1. I hope others are also getting it. R upon gamma minus 1. So NR upon gamma minus 1 dt. Now it should be very easy to integrate. Gamma is constant. Gamma is constant for a gas. R is universal constant. Moles are constant. So when you integrate, these all are going to come out very easily. Temperature, let's say from T1 to T2. So we have nR times T2 minus T1 upon gamma minus 1. This is the formula for work done in an adiabatic process, adiabatic reversible process. Any question, let me know. A direct formula based problem. Adiabatic reversible expansion. It is polyatomic. You see, monatomic, diatomic, etc. These things are useful for gamma. But anyway, gamma is given in the question. So no need to worry about this. Moles is 1, temperature is minus 50 10 atm to 1 atm. Okay. So look at this formula. P1, T1, P2. This is the initial thing. Now, T2 is not given to you, but that's no problem. Other things are nR upon gamma minus 1. No problem, no problem, no problem. T2. PV to the power gamma is constant. Here we want P and T relationship. We don't want volume. In place of volume, T upon P. T upon P. That will be constant. That means T to the power gamma, P to the power 1 minus gamma, that is constant. That means T1 to the power gamma, P1 to the power 1 minus gamma equal to T2 to the power gamma, P2 to the power 1 minus gamma. P1 and P2, their units are same. Units will get cancelled. P2 upon P1. We want T2 to the P2. So T1 to the power gamma, P1 upon P2 is 10 to the power 1 minus gamma. That is minus 0.33. And therefore T2 equal to T1 divided by 10 to the power 0.33 upon gamma, that is 1.33. Now, T1 is never used centigrade. How much is that? 273 minus 15, 223. The 223 divided by 10 to the power 0.33. 0.33 upon 1.33. Let's keep it like that only. Now what done is n is 1. Let's say we want answer in joules. So taking R equal to 8.314, gamma 1.33 minus 1, 0.33, T2 minus T1, 223, 10 to the power 0.33 upon 1.33 minus 223. 223 goes out. So 8.314 into 223.33. Now that calculation, suppose that is given to you, I am giving that to you, 10 to the power 0.33 divided by 1.33. That is 1.77059. Let's say 1.77 minus 1. Let me recheck. Looks okay. Now this will be 8.314 into 223 divided by 0.33 multiplied by minus 0.77 divided by 1.77. Can you calculate this? Minus 2444, yes.